Yo, what is up, guys? We're back at this. The fast inverse square root Quake 3 algorithm.
Hi, and now we want.
So there was this thing in the last video that I wanted to do a little bit of a diversion into and see if it goes anywhere. So yeah, the last time there was this part. Let's see.
Bro, small values of x, log is an approximation to log of 1 plus x. For small values of x, log of 1 plus x is approximately equal to x. If you think about it, this approximation is actually correct for x equals 0 and x equals 1. But we'll add an additional term, mu. This correction term can be chosen freely. Again, with mu equal to 0, this approximation is correct at 0 and 1. But it turns out that setting mu to this number gives the smallest error on average for numbers.
So yeah, the smallest error on average.
0 and 1. So going back to our average.
Yeah, so I wanted to see how we could maybe discover that or find that. So it was kind of like it's like, how do you actually do that? It's like, all right, we have the function, we have these like two functions here. We have like y is equal to log base 2 of 1 plus x. And we have this function y is equal to x plus mu. And so we want to find the mu that minimizes the difference. Find a parameter mu which approximates this function the best from the range 0 to 1. So it's like, so it's kind of like along the way, we just take these little distances between these two functions and find the mu which minimizes that distance. So for any given mu, like if we actually fix mu, then it seems like if we take the integral from 0 to 1 of this first function here, log base 2 of 1 plus x. Oops. Minus x plus mu dx. If we take that and we, yeah, I mean, just for like a fixed value of mu, like we could evaluate this function and get a number. And I don't even know if we have to like mess with taking absolute values and stuff because, well, yeah, I don't know if we have to mess with taking absolute values. Like, it's not clear to me that we do. Yeah, I'm just gonna leave it like this for now. But yeah, we want to choose the value of mu, which makes this some smallest, because if we chose a mu where the line was like up here, the difference would be, you know, like this value plus this value. Actually, it wouldn't be that. It would be like this difference plus this difference plus like this difference, like plus all these differences. These are big differences. So I mean, we're doing log base 2 minus this, so we would be getting like some high negative numbers. Oh, okay, so that's where the absolute value would come in. Like, we don't want to minimize it and get like a huge negative value, like negative infinity. Like, we would choose like this line way up here. Yeah, okay, that's where we want to take minimize the absolute value. So if we take the absolute value of the whole thing. That doesn't change this integral that we would evaluate. It might change the optimization, perhaps, because we're taking like the absolute value of some function. But I don't know. Let's just look this up for now. So the last time I was watching this video, I was like, I'm gonna have to like break out a Calculus 2 textbook or something. But then I remembered, I'm like, oh, we just have, let me keep this up for now. It's like, oh, we just have ChatGPT. So we could ask like, how can I evaluate integral from 0 to 1 of log base 2 of 1 plus x minus x plus mu dx, where mu is a constant. Curious what it'll say. Let's see. Log base 2 of 1. Yeah, okay, got it. Rewrite it in terms of the natural log. Oh man, I haven't seen this trick in a really long time. Wow. This is like, yeah, we can get rid of the annotation stuff now. Wow, yeah. Can rewrite this in terms of natural logs. I don't even, it's been so long since I've seen this. I have no intuition for why this actually works. But it's saying, all right, given that we can do that, it's like, all right, that thing is equal to, all right, so it rewrote this as, okay, a natural log, and we just like pull out the constant thing here. Okay, and we split it up into two integrals because an integral is a linear operator. It's kind of interesting. Okay. So we're able to, interesting. Okay, we're just able to pull it out, split it into two parts. Okay, we just like split this up again. Evaluate each term. The log one, integration by parts. Let's go. Set u is equal to this, du is equal to this, dv, v is equal to x. Let's fucking go. So then integration by parts. It's du. Oh, okay. So it's doing du. It's like, what's the integral of this? No, what's the derivative of this? Which is this. So I guess the integration by parts thing is like, where's the x times natural log of x? Where is x? It's v times u, maybe? It's like v times u minus the integral of du dv. That sounds familiar. Simplify the second term. All right, the integral of this, well, we're just doing some algebra here. X over 1 plus x is equal to, how does he do that? 1 minus? I don't see how you can do that, but okay, so Okay, like assuming that this is equal to this, you could split it up again. You got 1 over 1 plus x. I guess the integral of 1 over 1 plus x is easy to integrate. Combining, we get this. It's, oh my God. Wow. So we're evaluating all these integrals at different locations. Evaluate this. Evaluate all these individually. Oh my, this is crazy, yo. Simplify. So, and finally it's saying it's equal to 3/2 minus 1 over the natural log of 2 minus u. Wow, that's crazy. So, all right, there's a closed form for it. That's crazy because the two functions that we were comparing was a log base 2, like the log base 2 and log base 2 of 1 plus x and x plus u. So we do have a kind of like log 2 thing still in here. And we have the u, but, oh yeah, and x, x just ranged from 0 to 1. So we shouldn't expect to see any x in here left. So, okay. So then we're just like, all right, so what's the value of, okay, so this is saying like, no matter what value of mu that you pick, this is going to give us the difference of, yeah, the difference of log base 2 of 1 plus x and x plus mu over the range of 0 to 1. So now I'm curious, yeah, with the absolute value thing, like say we want to minimize some function. How about like say we want to minimize that function, the resulting function of mu, to pick the value of mu which makes the absolute value of that expression as small as possible. How would we do that? Yeah, take the minimum over mu of that thing, analyze the absolute value function. Is minimized when, yeah, this thing is equal to 0, sure. Solve when this thing is equal to 0. That's true. It is minimized when this thing is equal to 0. So if we just set it to 0 and we solve for it, we get 3/2 minus 1 over the natural log of 2. We got 0.057. Is that what they say here?
For numbers between 0 and 1. So going back to our formula,
It's pretty close.
But it turns out that setting mu to this number gives the smallest error on average for numbers between 0 and 1.
That's weird that it's not exactly the same. It's saying mu is approximately, like let's actually do it exactly. So let's say, why is it saying approximately? 3 minus, 3 minus, what? Let's go. 3/2 minus 1 over the natural log of 2. That's it. 0.057. Yeah, I don't know. I'm pretty fine with not getting the exact right answer. I just wanted the intuition, like the major steps of what we would do to come up with that number. I'm fine with that. That was cool. So it's integration by parts, and yeah, just evaluating that integral, evaluated to that closed form. It's interesting, the closed form. It's like, what is a closed form? Like, what's not a closed form? The not closed form thing, I guess, is like, yeah, I never really thought of it like this, but not a closed form is like an integral or a sum. It just means like you actually have to like run like the summation um, to actually evaluate it. Like you can't just plug something in. It's almost like closed form means it's big O of one, like runtime, and not closed form means it's like big O of n or whatever. Interesting. Or like n squared if it's yeah, like two sums.
So it's
All right, so now let's actually get here to this next part of the video.
the first step is actually not complicated. It just looks complicated because it's memory address trickery. So we stored our number into y, and now we want to do cool bit manipulation tricks.
What number is y though? It's all right, let's open this up. So y is just okay. So y is just the number that we want to take the inverse square root of.
Let's think about what we just did. Scale with the 3. The first step is actually not complicated. It just looks complicated because it's memory address trickery. So we store a number into y, and now we want to do cool bit manipulation tricks. Floats, unfortunately, don't come with the tools we need to do bit manipulation. The reason you cannot do bit manipulation on floats is that they were never designed to do so. Floats are inherently tied to the IEEE standard 754. Longs, on the other hand, were designed to do bit manipulation on them. For example, here's one trick. Bit shifting a long to the left doubles it, and bit shifting it to the right halves it. And yes, if your number is odd, you do end up rounding. But hey, we're willing to accept such inaccuracies, as long as this means that our algorithm is fast. C, as pretty much all programming languages do, provides a way to convert from a float to a long. This conversion does what most programmers needed to do, namely convert from a decimal number to an ordinary integer as best as it can do. So if we give it a float like 3.33, it converts it to an integer, in this case 3. But this is not the conversion we need here. First of all,
wow, so it actually that's interesting. It's actually doing a lot. It's actually doing a lot under the hood there to actually do that. It's actually like moving the bits around and stuff.
We don't care about the resulting integer number. We want to somehow keep our float. And secondly, the bits that lie behind our number get all messed up. We don't want this conversion to mess with our bits. The only thing we want to do is to put the bits 1 to 1 into a long.
So yeah, let's just look at it and see if we can kind of figure out what it's doing before he says. So this Yeah, that's fine. So this thing here. So we take the address of y. So we start off with y. So y is just a float. It's like y is a float, and then so then we take the address of y, and that gives us a pointer, like a variable of type float pointer. So that just gives us a pointer to the float. And so that's that like address of y thing here. And so then we just cast it to a long pointer via the long pointer thing. Via the long pointer. And then we just dereference that to get a float back. What is that? We just dereference it and we get the float back. Like what is so what is I? Oh, I is a long. Huh. Okay, that's interesting. So we just convert it to a long pointer, and the long pointer is like, all right, yo, this is just pointing to a long. I guess all it really knows is like, yo, a long is 32 bits, and like here's 32 bits. So just like point to this thing. And then you can like dereference a long pointer, and it's just like the bits. So that gives us I. Oh, okay. Doesn't seem too bad.
The way you achieve this is to convert the memory address, not the number. First, we get the address of y. This is the address of a float. Then you convert that address from a float's address to a long's address. The address itself doesn't change, but C now thinks that the number living at that address is now a long. So then you read what's written at that address. Because C now thinks that this is an address of a long, it will read that number at that address as if it were a long. Like this, we tricked C by lifting the conversion away from the number itself to the address of that number. And that's how we get the bits of a number into I. I don't know what else to say. That's just how C works.
Yeah.
So let's just go to the next step.
Nice. Okay. That's pretty cool that I guess we're 1 out of 3 of the way there. So it's like this step is basically done. The evil floating point bit hack. All right, what the fuck step? Oh, okay, this is probably just, I don't know if it's that constant. I don't know, we'll see, I guess. This thing divided by 2.
The intuition behind the second step is the following. Remind yourself, bit shifting a number to the left doubles it, and shifting it to the right halves it. But what would happen if we did something like this to an exponent? Doubling an exponent squares the number, and halving the exponent gives us the square root. But now also negating the exponent gives us 1 divided by square root of x. That's exactly what we need. So let's remind ourselves what our goal is here. We have our number stored into y, and our goal was to calculate 1 divided by square root of y. As I've already said, calculating this directly is too hard and too expensive. But we've extracted the bits from y, and we've seen with the IEEE standard 754 that the bits of a number are in some sense its own logarithm.
No, not in some sense. Okay, what was it? It was like within the bits, you can use that and apply some constants to it, and you can get the logarithm. It's close.
That means in I, we have stored log of y, up to some scaling and shifting.
Yeah.
I claim that our problem becomes way easier if we work with logs. Instead of trying so hard to calculate 1 divided by square root of y, we instead calculate log of 1 divided by square root of y. We rewrite this to log of y to the power of minus a half, so we can take out the exponent. Calculating this is stupidly easy.
Oh.
You might think, oh no, we have a division in there. Didn't you say in the beginning that divisions are slow? Well, yes, but remember that we can do bit shifts now. Instead of dividing by 2, we just bit shift once to the right. This already explains why we do minus I bit shifted once to the right. But why is this not
minus I bit shift to the right? Okay.
0x5f3759df here again? Well, because our logarithm is actually scaled and shifted. So let's calculate and understand where it comes from. Let gamma be our solution. Then we know that log of gamma equals to log of y to the power minus a half, which equals to minus a half times log of y. Now we replace the logarithm with the bit representation.
Replace. Wait, what?
And then we just solve for the bits of gamma. I'll spare us the details, but this is the result. The magic number turns out to be the remnants of the error term mu, the scaling factor, and the shifting. Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from shifting.
Let's look at this.
Representation of times log of y. Now we replace the logarithm with the representation.
Replace the logarithm with the bit representation. Yeah, because it was like to compute log of a number. It's like to compute log base 2 of a number is basically equal to, I think it was log base 2 of a, yeah, it was basically log base 2 of a number where that number is in scientific notation or the IEEE thing. So we kind of started with like the mantissa and stuff. And we just took the log base 2 of that, right? We can kind of like go back in the video and see it. Is this thing up here?
7 subtracted from it. Number behind the bits with this formula.
So we basically have the mantissa and the exponent in hand, like in our float. And okay. And like this is what the number actually represents in the float. So like this thing here is like this is y, like this is number, like this is the thing that we get passed in. And then so we say we take the log of that, right?
This should seem familiar to you. And now algorithm of that expression.
Take the log of that, and then we all right, let me even just take the screenshot of this. This can't get any thinner. It's not that bad.
It's doing computer science.
Okay.
Here.
So got that. Go forward. I guess
by some constants.
Equal to this thing. So like log of our number, like log of y. Yeah, log of our number is equal to this thing. That's what the number would be.
So in some sense, the bit too hard and hard to calculate one is to log of y to the power of minus a half, so we can take out the exponent. We have a division, remember, to the right. right. Well, understand where that log is a half gamma. Let gamma be our solution. Then we know that log of gamma equals to log of y to the power minus a half, which equals to minus a half times log of y. Now we replace the logarithm with the bit representation.
Replace the logarithm with the bit representation. So let me just go back in the video and grab that screenshot of the yeah, okay. I mean, that's what it evaluated to. I get both of these. Okay.
Plus e convert the number. First, we get the half, so we can take out the exponent. Calculating this is stupidly easy. You might think, oh no, we have a division in there. Didn't you say in the beginning that divisions are 0 times log of y? Now we replace the logarithm with the bit representation.
The bit representation. So you basically have y, and from y, you can grab the mantissa, you can grab the exponent, and you basically just say, all right, the mantissa plus this times the exponent. I mean, that's the actual value of it. So basically you just replace log of y with like this thing. Yeah, and I guess he's calling it like the mantissa of y and the exponent of y. Okay. Yeah, okay. So it's like gamma has its whatever gamma is, it has its own mantissa and it has its own exponent, and whatever y is, it has its own mantissa and has its own exponent.
And then we just solve for the bits of gamma. I'll spare us the details, but this is the result.
So you solve for the bits of gamma. Like he said the bits, like it's like literally like the bits. Like you want the bits of gamma. So you want the mantissa of gamma and you want the exponent of gamma, so you can like form the float of gamma. Yeah, we'll see where he goes with this.
The magic number turns out to be the remnants of the error term mu, the scaling factor, and the shifting. Now we have the bits of our solution.
Okay, I'm kind of lost so what does he actually do here? What actually happens? I mean, just kind of like from being in the code, like you do have the mantissa of y, like that you can just pull out, and you've got the exponent of y that you can pull out. Mu, we like solved it before. It's that value like 0.04, like whatever. So you can just evaluate this thing and you can get a number. Like, I don't know, this number is like whatever. It could just be this. And so now we're saying that the mantissa of gamma plus 2 to the 23rd. Okay, so that's just the value of what gamma is. Oh, okay. And the whole point of this is we were solving for gamma. Like we set, like before we set gamma is equal to 1 over the square root of y. And so we solved for gamma, like we solved for the mantissa and the exponent. So if we just calculate this, and we basically say that, like in C, if we just said like float of gamma is equal to like this expression here, then it's kind of weird. Like we don't even need to do floats. Like we could do long, we could do whatever. It's just a number. I think long is like an unsigned thing. I think it's just kind of like an int. So we kind of need a float just to store it. But yeah, the important part is like this is literally the 1 over the square root of y. Like this number is the answer because it's equal to, yeah, the mantissa of gamma plus its thing here. So okay, and I recall that where did I come from? I was like, the number went into y, and then like I is like the long version of y, just go the long version of number. So I basically is y. That's crazy. Like if, oh wait, so this value here, right here, is y. Okay, so we just take, okay, cool. So nice. So I didn't realize there was such a one-to-one correspondence between this. So like literally like this thing, yeah, it's even color coded. Yeah, this thing is just I. This shifting over is just the division by 2. This minus is the same. And then this is just a constant, which is this right here. Mu is like 0.04, blah, blah, blah. So you just evaluate that. Cool.
Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from those bits. Well, actually, not the exact solution, just an approximation. This is why we...
Let's just go back here. So So okay. So like I is the solution, and then yeah, we just cast it back to a float pointer and then get the value back out. Y is type float. Okay.
Actually, not the exact solution, just an approximation.
We did copy the bits from Y into I, and then I guess like I, and then we like modified I, and then we went back to Y. Okay.
Well,
it's kind of like we started off with I don't know. We kind of like copied them over into Y. We like did some stuff here, and then we copied them back over into I.
not the exact solution, just an approximation. This is why we need the third step. After the previous step, we have a pretty decent approximation, but we did pick up some error terms here and there. But thanks to Newton's method, we can make a really good approximation out of a decent one.
Where are the error terms? I don't quite. Oh, okay. Remember we divided by 0, and yeah, it's not exactly. Yeah.
Newton's method is a technique that finds a root for.
Wait, one thing that's weird is we divided by 0, or we divided by 2, but we divided an IEEE thing by 2. We just shifted those. That doesn't. I feel like that doesn't make sense. We divided I by 2, and I was just like I is an IEEE like Y thing. Doesn't feel like it doesn't make sense to just divide that thing by 2. I feel like you would want to divide the mantissa by 2. Oh, maybe that's where he was. Maybe that's where he was talking about whatever. I think I'm gonna call it for tonight. It's like 9 o'clock. I think I'm gonna call it. Thanks, guys. I will see you next time.